This is Donna Nelson at the University of Oklahoma, and I am filming my lectures for organic chemistry. In this organic chemistry course, I am using the textbook by David Klein, and we're covering Chapter 2. So let's look at the material included in Chapter 2. First, we're going to have 3 different lectures coming from Chapter 2. First, molecular representations. We'll look at the bond line structures, identifying functional groups, carbon atoms with formal charges, identifying lone pairs, and 3-dimensional bond line structures in this first lecture. So let's look at this. Here are the different ways that you may see molecules represented in this course. So here is a Lewis structure. You can see the pairs of electrons on oxygen. You can see a partially condensed structure where the methyl groups, the CH3, is actually drawn as CH3 instead of the individual bonds. Then there's the condensed structure in which the 2 methyl groups are not written separately. And then there's the molecular formula, C3H8O. The molecular formula is inadequate. The molecular formula is inadequate to distinguish between, say, propanol and isopropanol, or even ethyl methyl ether. And so it is necessary to use one of these other molecular representations, even in order to be able to see what types of functional groups there are in the molecule. So here are 2 different types of drawings of the same compound. This compound up above is exactly the same as the one down below. And this shows very easily why it is that we don't use Lewis structures very often. In the Lewis structures, notice every single CH bond is drawn and every electron pair is drawn in as well. We're not usually that interested in CH bonds unless they happen to be reacting in the particular reaction that we are studying or trying to use. And so here you see the CH bond is missing. It's understood that it's here. So every one of these CH bonds that's missing, one would need to be able to know that it's there, even though it's not drawn in. The reason that this bond line structure is used is because the chemistry typically is going to be done at or next to functional groups. And so by drawing the bond line structure, the functional groups really pop out at you. Up here, they're just sort of buried in the rest of the clutter. But here, the functional groups really pop out at you. And since chemistry is going to be done at the functional groups, it really helps to be able to just look at one of these bond line structures, and your eye can just sweep across the structure, and you will know instantly what all functional groups are there. And that is what is important, because whatever reagents are added to the molecule, the reagents will be reacting with the functional groups. The carbon skeleton doesn't change that much. It's somewhat rare. So how to read bond line structures. This is a bond line structure for just hexane, a relatively simple molecule. And you'll see that there's a carbon at each corner or end point. At each of the vertices, there's a carbon, 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 carbon. Same thing here in this alkene, and you can see the carbon-carbon double bond. You can see it's the same way in this alkyne. There is a carbon at each end point of of each bond. So the zigzag formula, the zigzag format rather, is somewhat accurate. So remember the bond angles are 109 and 120, 180. And so by drawing these bond line structures, the drawing gives a good representation of the actual bond angles as well. The CH bonds that are attached to every carbon are typically not drawn. And so it's left up to you, the student, to learn and therefore to know that every carbon will need to have 4 bonds. So here at carbon 1, there's only 1 bond shown. That will automatically tell you that there are 3 other CH bonds here because there's no charges and only 1 bond is shown. Since carbon always has 4 bonds in the ground state, then 4 minus 1 is 3. That tells you that there are 3 CH bonds. Similarly here, this carbon has 2 carbon-carbon bonds. That tells you that there are going to be 2 CH bonds at every one of these vertices or corners. So you must remember when looking at these bond line structures that the carbons will always have 4 bonds. So here, 1, 2, 3. 3 bonds are shown as carbon-carbon bonds, and so that means that there's going to be 1 CH bond that is not drawn in. And this is purely typical. So it is appropriate to draw the structures out linearly like this, showing all of the CH bonds. However, that's very cluttered. It takes longer to draw these, and so we chemists typically use these bond line structures. Notice the CH bonds are missing, but they are understood. They are there. And so this linear structure really is more accurately drawn as this zigzag structure. And so this is really more accurate. It's faster. It gives the chemist who is trying to do something with these molecules, it gives information faster. And so a person who is educated in how to read these can read them much faster than they can read that, and they get just as much information. You can practice identifying the location of carbons and hydrogens in these skeletal structures. You should be able to just know where the CH bonds are located and how many CH bonds are at each carbon. So for example, this carbon has 3 carbon-carbon bonds, so there's going to be 1 CH bond. Analogously here, 1 CH bond, 1 CH bond. And you should be able to look at these and know how many carbon-hydrogen bonds that will be drawn. Notice if there is a sulfur hydrogen bond or an oxygen hydrogen bond, those bonds to hydrogen are shown. Those protons are shown because that's considered part of the functional group, and the functional groups are always drawn in. When drawing double bonds, you should take some care to draw them in a way such that the bond angles are at least approximated. So the bond angle here in the carbon-carbonyl bond is about 120, so you definitely would not draw the molecule like this. This is about a 60-degree angle, and actually this is much closer to that found in the actual molecule. So this is a good depiction. This is a poor structural depiction. When drawing single bonds, remember that there is free rotation about carbon-carbon single bonds. So this group that is shown pointing up could just as easily point down because there's free rotation about these carbon-carbon single bonds. So this drawing is equivalent to that because this methyl group can rotate down here. So these two are equivalent. They are different conformations of the same molecule. All heteroatoms, that means atoms other than carbon and hydrogen, must be drawn in. Otherwise, there will be no way to know what functional groups exist in the molecule. And the protons attached to those heteroatoms are always drawn in. And you never draw more than 4 bonds to a carbon atom. There may be fewer than 4 bonds, especially if you have a positive charge or a negative charge or a radical. If the molecule is a carbocation or a carbanion or a radical, but you'll never have more than 4 bonds to a carbon. That goes straight back to the octet rule. The carbon being surrounded by 8 electrons and being surrounded by 4 bonds. Since there's 2 electrons in each bond, that respects the octet rule. Now, another reason for having bond line structures or using bond line structures is that it makes it so much easier to recognize the reaction that either is going to take place or has taken place. As I mentioned earlier, one's eye goes straight to the functional groups. That's where the chemistry is going to take place. And so here we can see the carbon-carbon double bond, which is the functional group. And then you can look at the product and see that the carbon-carbon double bond is gone. And so therefore, H2 has added across the carbon-carbon double bond. And so that functional group has been reacted. Up here, it's much harder to see because there's just, the CH bonds are just clutter. So we will use the bond line structures extensively. It will be very necessary for you to know what those bond line structures are, how to read them, how to draw them. This is table 2.1 from your textbook. The functional group, this functional group is an alkyne. Here's an example of a molecule that contains the alkyne. It's found in chapter 9. So this tells you, this gives you all of the, not all, but many of the important functional groups in which chapter they'll be found in, going all the way up to 22. This is an amine. Here's an example of diethylamine. And actually, chapter 22 is the last chapter that we cover in Org 2, using this same textbook. So you will get through 9, 12, and possibly 13 in Org 1, which is what this class is. But it's still a good idea for you to learn these functional groups and what classification they belong to. In other words, what family, what chemical family they belong to, and to recognize the functional group in a molecule. It's a good thing for you to know these because you'll be seeing, even though you won't cover these exact molecules, you'll see them as reactants. And so it's important for you to know what they are. A lot of times students will say, do I have to learn those names? I don't know about sitting down and memorizing them, but if you're taking organic chemistry, and especially if you're taking Org 2, it will be necessary for you to know these. If you try to avoid learning them, then, that's up to you, but you will have a gap in your knowledge, and you may feel like you didn't learn everything that you needed in this course. And then when you go away and try to take entrance exams to get into, medical school or dental school or, another university, if you haven't learned what you need to learn, then, you might not be so happy with the outcome. And that is entirely up to you. It is entirely up to you how much you learn. I'm filming these lectures so that you can have them available to you 24/7, and you can watch them as many times as you want. You can stop them and read something or work out a problem and come back and start them up again. It's all in your hands. And so what you do with these, whether you ignore them or make great use of them, that will determine how much you learn. So carbon atoms with formal charges. One example is a carbocation, where a carbon is bearing a positive charge. Now it has a total of 3 bonds. It's lost a pair of electrons, and so it has lost a bond when it lost that pair of electrons. So here there is no CH bond because the 3 bonds are shown. Here only 2 bonds are shown, and so there is going to be a 3rd bond. There will be a CH bond at that carbon. Here only 1 carbon-carbon bond is seen, and since carbon has 3 bonds when it is bearing a positive 1 charge, then that tells you that there are 2 CH bonds at that carbon. A carbanion also has 3 bonds, but it also has a lone pair. Up here, there is no lone pair. There is an empty orbital. Here, there's 3 bonds attached to carbon, but there is a lone pair that occupies another orbital. So this carbon is surrounded by 8 electrons, 2, 4, 6, 8. It has the stability of a Phil.Tet. Up here, the carbocation, let's use this one. This carbon is surrounded by only 2, 4, 6 electrons. It is electron deficient. So that tells you how these are different. We'll look at that more in later chapters. Formal charge. Okay, sometimes this becomes confusing, and so I have drawn out some answers to this question that is asked. Formal charge, section 1.4, it was covered. It affects the stability and the reactivity of molecules, so you must be able to identify formal charges in bond line representations. The following structure is incomplete because the charges are missing. Formal charges must always be drawn in order to have all of the information. And so the way that this is calculated is one starts with the family that the atom belongs to. Let's consider this oxygen. This oxygen belongs to the family, the periodic table family number 6. And so in order to be neutral, it needs to be surrounded by 6 electrons. And so you can see here that actually this oxygen atom is surrounded by 7 electrons. It's surrounded by only 5 electrons that it owns. It owns the pair of electrons here. That's 2. So it only 1 of the electrons in the carbon-oxygen pi bond belong to oxygen. The other one belongs to this carbon. 1 of the electrons in the carbon-oxygen sigma bond belongs to oxygen, the other one belongs to carbon, and only one of the electrons in the oxygen-hydrogen bond belongs to oxygen. And so here, this oxygen, it only has 5 electrons surrounding it. It really should be surrounded by 6. So it's bearing a positive 1 charge. And so you can go back and review the way that formal charges are calculated. And so you're going to see that there's going to be a +1, a -1, and a +1 on this molecule. Bond line structures, the formal charges must be drawn, but drawing the lone pairs is optional. The lone pairs are often not included. So here, this is an anion. The negative charge is shown on oxygen. Oxygen is in the 6th group. It needs 6 valence electrons. Here, this oxygen anion actually has 7, 2, 4, 6, and then 1 more from the oxygen-carbon bond. This oxygen-carbon bond, 1 electron belongs on oxygen, 1 electron belongs on carbon, because this oxygen-carbon bond is taken as belonging to both atoms. So this oxygen is surrounded by 7 electrons that will be, each electron bears a negative charge. And so it needs 6 valence electrons to be neutral. So this oxygen is bearing a charge of -1. Oxygen has 3 possible bonding patterns. It can be negatively charged, or it can have no charge, or it can be positively charged. The same 3 patterns as for any second row atom with 5, 6, or 7 valence electrons. So let's look at this. If there is 1 bond and 3 lone pairs, 1 bond and 3 lone pairs, that's 2, 4, 6, and then 1 electron from the bond. So here oxygen has 7 valence electrons. You would still, in trying to decide whether it has the stability of a filled octet, you would still say 2, 4, 6, 8. But in this calculation, we're not interested in whether it has a filled octet or not. We're talking about valence electrons. And so the electron pairs, the non-bonding pairs, are both counted as valence electrons, but only one of the electrons in the CO bond is counted as a valence electron. So that hopefully clears up a possible point of confusion. So for valence electrons, oxygen is considered to be surrounded by 7 electrons. Here, this oxygen has 2 bonds, so 1 electron from each of those bonds. That's 2 electrons contribute to the number of valence electrons, and then we have 2 lone pairs, so that's 4 more. So the 2 from the bonds and the 4 from the lone pairs, that's 6. And so here this oxygen will have no charge. When oxygen has 5 valence electrons, let's look at this. So it has 1 lone pair, that's 2, and then 1 from each of these bonds, that's 1, 2, 3 valence electrons coming from the bonds, 2 coming from the non-bonding lone pairs, and so that's 5, and so oxygen needs 6 to be neutral, so this is bearing a positive charge. And the same thing goes for nitrogen. It's the same discussion, and so I'm going to let you go through these, and if you have any questions, you can ask in class. But this, the calculation, is analogous to what you saw on the previous slide. All molecules take up space in 3 dimensions, but it's difficult to represent a 3-dimensional molecule on a two-dimensional piece of paper or a blackboard or a screen. So dashed and solid wedges show the groups going behind the screen here or coming in front of the screen. This one is going behind the screen. This one is coming in front of the screen. This one is going behind the screen, in front of the screen. And this bridge in this bicyclic molecule is coming out of the screen. So this, see how it's coming out and then coming down? And so there's an angle here. So this is CH2. This is a methylene group, a CH2 group that is coming out of the screen toward you. So this is acyclic, it has no ring. This is cyclic, it has one ring. Bicyclic, it has two rings. 1, 2. Other ways to show a three-dimensional structure. So this Fisher projection by just standard, any of these groups that are attached across the molecule are coming out of the screen. So this CH bond, it's just standard notation. This CH bond is coming out of the screen. This OH bond is coming out of the screen. This one's coming out of the screen. This CH is coming out of the screen. This one is coming out. This one is coming out. All bonds that go up and down are going back into the screen. That's for Fisher projections, when Fisher projections are used. And so it should be very easy to recognize these Fisher projections. Although it may not be necessary to actually know the word Fisher, but you should be able to recognize the drawing. Same thing with Haworth projections. It's not necessary that you know the name, but it is necessary that you be able to recognize the drawing and what it means. And so here the wedge, solid coming out, that means it's coming out at you. This is wedged out. This bond is darkened in. It means that this bond is closer to you than the bond back behind. So it's drawn in a way such that it has some three-dimensional quality to it. Notice that the carbon-oxygen bond is going up. Here the CH bond is going up. And you can see a little break drawn in the bond back behind. Here there's another little gap in the middle of the bond drawn behind. And so that tells you that this carbon-oxygen bond is in front of that carbon-carbon bond that's drawn behind. Here the CH bond is drawn in front of the carbon-carbon bond that is drawn back behind. And here this is another, again, we're depicting a bicyclic compound. And so once again, you can see the CH2 group that is the bridge coming up. And you can see that the line is going in front of this broken line. That's indicating a bond in front of this other bond that is back behind. So if you see that gap in there on either side of the line, that means that there is a bond back behind. And so this is depicting the one bond in front of the other bond. So it's important to be able to draw these and to be able to recognize them, because the shape of the molecule can influence how it reacts, especially in biologically different settings. So that is the first lecture on molecular representations. And so now we will go on to more information such as resonance structures.